Good morning, everyone. I see some good mornings coming through in the chat. Dr. Ford, our HOD, Dr. Maynard Cates, Dr. Gordon Smith. We have Kellyanne who is sending hello. Okay, it is 3 minutes past 11. What time is it there, Michael?
3 minutes past 12. Here
3 minutes past 12 in St. Augustine, and I say good morning, everyone, and welcome to the Thursday seminar series right here in the Department of Chemistry at the UWI Mona. It is my pleasure to welcome all of you from wherever in the world you are joining us. I want especially to welcome the colleagues who are joining us from St. Augustine, here to support Dr. Ford as he shares with us this morning. So I tell you a little bit about Dr. Michael Ford, who is our speaker this morning. Dr. Ford holds a PhD in heterogeneous catalysis, was awarded in 2012 from Cardiff University. And before that, he completed the MChem with industrial experience in 2008. That was at the University of Edinburgh. During the MChem with industrial experience, there was 1 year that he spent as a research scientist with Procter & Gamble at the Rusham Park Technical Centre in the UK. His PhD studies was funded by Dow Chemical Company under the Dow Methane Challenge, which set out to find new green routes to convert methane into methanol. His postgraduate research was conducted, like I said, at Cardiff University at the Cardiff Catalysis Institute, and he worked under Prof. Graham Hutchins, Fellow of the Royal Society, before returning to take up an academic position at the UWI St. Augustine. His research interests generally lies at the frontier of heterogeneous catalysis and materials design for heterogeneous catalysis and green chemistry. Primarily, his current research encompasses selective CH bond activation in lower alkanes like methane and ethane using zeolite catalysts, and now extended to MOF materials or MOF catalysts. Catalytic transformations of biomass-derived platform molecules into fuel-blended chemicals using hydrogenation chemistry is also an area of interest for Dr. Ford. And he's also worked in and continues to work in the field of waste material utilization, specifically the use of end-of-life tires in concrete and road paving mixtures. I tell you, Dr. Ford is a pleasure to work with, ladies and gentlemen. I have had the pleasure of working with him. Recently, we've spent a lot of time working on Commonwealth chemistry from its inception to its formation, and now on the scientific organizing committee, where we are planning and about to get into the inaugural Commonwealth Chemistry Congress. We would have been in St. Augustine this year, but we have had to pivot to take it virtual. But a little bit else about the man. He is married, has no children as yet, and like I said, he's quite a pleasure to work with. He's also an entrepreneur. Not sure if he will mention any of that today, but today I ask you to give him a round of applause as he speaks to us on a topic entitled No Small Odyssey. We're going into Greek mythology here now, guys. Small particles, great impact. Dr. Ford, it is indeed a pleasure to introduce you, my friend, my colleague.
Thank you so much, Marvadine. And first, I want to check that everyone can hear me clearly and also see the presentation I have on the screen.
From my side, that's a yes.
That's good. Okay. And of course, not to take up too much bandwidth, I'm actually at the UWI at the moment in my office. And usually 1 out of every 5 times I'm here, the internet goes a little haywire in this building. So just to let you see who I am, Dr. Ford or Michael, I prefer to be called Michael. The doctor part is just one of the qualifications I've acquired through hard work and not necessarily doesn't actually tell you anything about me per se. But by the end of this talk, I hope you'll get to know a little bit about me and my approach, the way I think, and the types of things that I want to champion at the UWI and elsewhere in terms of catalysis chemistry, because I'm a catalysis chemist. That's what I am. That's what I know best, and that's what I do best. And of course, thank you, Marvadine, for your warm welcome and for the invitation to do this presentation. It was a bit of a bending of the arm because I assessed that I didn't have much time to put together something early in the semester, but here we are. And I hope that you'll all enjoy it and learn some things about what we do here in the catalysis lab in UWI St. Augustine. So the talk title is entitled No Small Odyssey. So it means that we're going on a little bit of a journey, a winding pathway that leads hopefully to some sort of green, beautiful pasture in the end, with some changes of fortune from very bad fortune to very good fortune, hopefully. And in particular, we're going to be talking today about small particles, great impact. And the small particles are nanoparticles. And so my research is focused on nanoparticles, single atoms on surfaces that can do transformations in a selective and at an economic manner. So just some background to my odyssey, my overall odyssey from the years from leaving, secondary school with your A-levels. My odyssey starts over here in Trinidad. Lovely Trinidad and Tobago flag is there. And of course, I put the flag a little smaller in the beginning than in the end down here because the odyssey has allowed me to have a different view of my home country. When you're in the Caribbean and you're doing your studies, the whole idea is, I want to go abroad and do some work. I want to be an international player. I want to, go to the top universities, etc. And so I also fell prey to that idea and decided I would go to United Kingdom to do studies, although not in chemistry. And that's the biggest part, I suppose, of my odyssey is I was actually thinking of political science or genetics. So that was my areas. I really love genetics and the idea that I could splice some genes in and maybe make myself green and do some photochemistry in my cells and end up making my own food. That was my childhood idea. And of course, as we all know, to go to the UK, the price of education was actually quite high. And so the odyssey started off with me not actually having the funding to go to the UK, even though I had scholarship. The additional funding was too much. And so I changed my plan and decided I would go to the US, and then I could only do chemical engineering there. Those were the offers that I was given. I was like, well, I don't want to do chemical engineering. I want to be a biologist, a geneticist. So maybe I want to do something in international relations or not necessarily chemical engineering. It turns out that I'm probably as close as you're going to get a chemical engineer in a chemistry department at the moment. And so this odyssey carried me over here down to Barbados. And I don't know if we have any Cavel people on here, but the Frank Worrell Hall, as the picture I chose, is one of those places that a newcomer to the Cavel campus will know because they're looking for accommodation, and it's going to be the place they meet all of the locals and all of the regional students. In this odyssey, I, however, did not stay at Frank Worrell Hall because I came to Barbados a few weeks early and actually found private accommodation. In fact, a whole flat, a whole house that I rented at the same price that people who were paying for Frank Worrell Hall and paying for rooms in there. And so I thought that was a very good start to my educational experience because I got a good deal for my money. And those who know me personally know that I am very astute with monetary matters. I love a good deal, right? And so I spent a year in Barbados, Cavel campus, very good year actually, very sound foundation. And then by some divine universal mechanism, I ended up in the UK right after that. So my first degree is actually from University of Edinburgh. And I went to the University of Edinburgh on some sponsorship that was provided by the Rotary International through the local arms of Rotary. as an ambassador, cultural ambassador. So I was going to do science. In fact, I was going to do genetics there, which was my first choice. And then at the same time, trying to talk about Trinidadian and Caribbean culture, because of course nobody knew where Tobago was in Edinburgh anyway. And when I went my first day, they said, well, we have to put you back down in year 1 because we can't look, you don't have your transcript and we don't know what you've done and we're not sure if the courses are equivalent. And I said, what? This must be madness. Better I go back. I'm not taking another year of year 1. And so I walked across the chemistry department for some advice and met my future director of studies, who is now retired. And he said, well, why are you doing that? Just come over chemistry. You'll do a chemistry degree. And I said, chemistry degree, I'm not really into that. And he said, why not? It doesn't matter what degree you do once you do it well. So I took his advice, did the chemistry degree, and ended up staying in Edinburgh for a while. And as Marvadine said, I went down here to Egham, just between Reading and London, halfway between Reading and London, to do my internship in the master's program with Procter & Gamble. And that internship went well for the most part from the scientific aspect, but not well from the social aspect because I didn't really fit into that culture very much. In fact, I don't think any Caribbean person fits into that culture very well in P&G at that site, which is now closed. But I learned a lot in that. And it turns out that the chemistry I was doing in the internship ended up being the same type of chemistry I was doing in my PhD in Cardiff and using hydrogen peroxide to create value. In this case, I was creating value from methane to make it into methanol. And then back again to Trinidad by some other divine mechanism, I suppose. And here I am at the end of this part of the Odyssey and now trying to build a new Odyssey in UWI. And the reason why I chose the word Odyssey is because, as you're aware, our particular research environments could be a bit challenging to get research done where new techniques, new equipment, new methodologies, new ideas are coming out that are not traditional or have not been explored in any detail at the UWI before. So you become a self-starter in that way. So it was a long winding road. It took many years, so 8 years of study. The road eventually led me back, and I used it to Trinidad, but I used the picture of the river because in the journey through your education, into your academic career, even if you want to go into industry, entrepreneurship, you always have to go with the tide, as it will, and trust that if you take the experiences and the lessons learned seriously, that you can always apply those to new situations and receive success. And in fact, in my entire career, looking back, I think all of the obstacles were actually very good for success in the future and set me up. So much so that I have a completely different way of thinking from most of my colleagues, I think, just because of the fact that I would have been in certain adverse situations along the Odyssey and made so many changes in what I was doing, but at the same time, had good lessons in each of those changes. And I think for those of you who are probably early career researchers, it's a good idea for you to sit and think very deeply and reflect upon where you were and how you're actually going to get the best out of whatever you're doing now. And that obviously goes for academics, since we do also struggle with research and other things as well. Okay. So I think that's about enough about that. And we're going to get into the talk. I will highlight some of the things I do in UWI so that you have an idea, since I know most of you are probably from the UWI and would have never met this Rasta chemist before. And then we're going to talk about some highlights, and just highlights because there's not enough time to go into the depths of everything that we do or have done in the research group, but just a few things so that you get an idea or flavor for where we're going. And of course, if you want to collaborate, you can also see where the opportunities are in this presentation for collaboration as well. So UWI, I put at the top of the list that I supervise MPhil and PhD students, 5 of them. And I put that as my top category since I am putting effort there. I really like to help people develop themselves. The undergrad degree is good for that. But of course, the postgrad degree helps people now develop into different caliber of person altogether. and it's a bit more intimate in terms of relationship between supervisor and students and providing your viewpoints and your concepts. So I do cherish that at the top of my list. And of course, undergrad teaching, as we were talking about at the start, before most people came in, I teach courses in industrial chemistry, green chemistry, sustainable energy. And this course we have here called Contemporary Chemistry that I'm now highlighting. It's actually, I suppose, a writing course, more or less, and a media course for chemists. So I do that, and I'm one of the persons who came up with this idea, and it's been well received. A lab instructor and also projects. Up to last year, I was a project coordinator, took over from Richard Taylor. He handed that to me and laughed. And now I've handed it over to Dr. Kumar and laughed as well. So one of the other things I do is coordinate the major in industrial chemistry, in which we have an internship. So we've instituted an internship program in the UWI, in our chemistry program here in St. Augustine. And the first interns were this group. And I should get some updated pictures of the others. But just to point out, in this group, this young lady here, Frida Kaufman, is a PhD student. And here's Alicia Jaffers, PhD student. These two are working in, I suppose you could say, industrial chemistry directly. And I'm not sure what Hezron is doing. This guy back here was a PhD student, and I'm not sure if he's still a PhD student. I think he stopped his at MPhil or something like that. So every year we get these bunch of students, they go out into industry, they spend a few weeks. It used to be 3 months, and now with COVID since last year, we've cut it down to only 1 month on an industrial project full time. And they gain a lot of experience in the working world, and not necessarily experience in difficult chemistry techniques, but experience in how to use their chemistry to get value in a product system, a system where they're making a product. And so we're very happy to continue that program and have people work with the persons from industry and build that. And we hope to get that program moving to have more students and more industry department collaboration in the future. So what do we do here? So we have a catalysis lab. And for every catalysis lab, you have to think about what is your concept? What is the concept behind what you do? I'm into green chemistry, and so sustainable catalysis is at the forefront. It's the center. This is the central idea. But when we look through the literature, a lot of people do catalysis that can be said to be sustainable, but there are some things that we believe are very important, because sustainable catalysis in a lab, in postgrad lab HNC1 building in St. Augustine, has to translate into something that goes beyond just a few bits of data that you publish. That's knowledge that people cannot necessarily get value out of. So I'm always looking at the value proposition for the chemistry. And we start, of course, with the product value, because at the end of the day, you need to make a product. If you have to sell it, whether it's knowledge or another physical product, you need to make a product. And in fact, 90% of all products that you buy or use in your lifetime would have seen a catalyst at some point, right? Or as a result, direct result of catalysis, whether it's sustainable or not. And so we're always looking at the product value. You see that in the presentation today. What's the product we can get and why is it valuable? But also, what's the value in the raw material? Because you need to take the raw material and make it into the highest value product in a particular type of way that will allow you to develop it further. Because in catalysis chemistry, we all want to have, a patent, and a patent leads to spin out company. And we know where the UE is with their AAA strategy or our AAA strategy. And so we're thinking about what raw materials we have access to and how we could use catalysis to transform those raw materials into valuable products. Of course, using green methods, because we want to be environmentally conscious, but we also want to optimize those methods. And from my research and understanding over the year, green chemistry is the way that we actually optimize the methods to develop products. And of course, we need to create knowledge, because that's what we do as academics, as chemists. We create knowledge, and that knowledge helps us in our quest to publish, to generate data, to have good products, to understand the system. It also helps other people to understand how to do better chemistry. So we go from the overall concept to the design concept. How do we design our system? And if you hear my talks or anything from any of my students, we all say the same thing. This is my idea in terms of design. Design has to be guided by some sorts of principles and also a flow of how the design works. It's in a circular fashion because all of these things are iterative. They lead to each other in a never-ending cycle. So there's always work for the catalysis chemist. We start off with material synthesis. We can make materials. And you have to understand, of course, when you make materials, how to make the materials and then what you've made. So this is how to make the materials. And then, of course, what you've made is the precise structure. And we use the word precise because, as I would show you, in catalysis, usually traces of a contaminant has a profound effect on the catalysis. And if you had a nanocatalyst with 2% metal on aluminum oxide, for example, it's highly likely that only a very small fraction of that metal or those metal nanoparticles are actually active for the main reaction that you're trying to do. So you actually need to have a lot of data to understand the precise structure and also to understand the reaction system. And I was just talking to one of my students about this, Ahmad, about this, who I think is probably listening, that when you move from one system to the next, the details of the system you have to really think deeply about that in order to understand how the catalysis is working, because what works in one system is not necessarily transferable to another similar system, whether by scale or difference in solvent or difference in temperature and conditions. And so you need to kind of understand what your reaction system is. And in general, we set the reaction system. So we set the conditions we want, and then we work the rest, which is synthesis, structure, and structure functionality relationship that you get when you understand the system and you understand the structure, the structure itself. Of course, then you can go back into optimization, which is material synthesis all again. So one issue with using this sort of approach is that you can have divergent research that continues on in many different directions, never having an end result. And when I did my PhD, I saw that with two of my colleagues and decided I would never do that at all. I would make sure that I kept the target in mind and I worked towards that target and try to not deviate into too many side projects trying to understand things which had nothing to do with the target that I wanted. In fact, I know one of my colleagues had to spend an extra 3 months finishing up his PhD. And because he had an arrangement with his government for financing, he got a whole 5 years added on to his compulsory service for those 3 months in Malaysia. And so I said, listen, I would never do that. I want to make sure that I keep the time and I get the work done in the best manner, the most efficient manner. So sustainable catalysis, and we want to do heterogeneous. We don't go into the homogeneous stuff at all in our labs. And one of the reasons for that is that we don't like homogeneous catalysis per se for bulk synthesis because of the issue with recyclability and stability of the materials, energy cost to get the product out of solution, etc. But also because we don't have some of the equipment that will be required to do homogeneous catalysis, proper glove boxes and extensive setups with strength lines and stuff like that. We do catalysis by design of materials, but also on understanding how the synthesis itself affects the material structure. So we don't want to use techniques that I call hammer techniques, which is you hammer the thing into place. We want to be able to take a fine nose tweezer and put a particle on a surface. That's what we want to do in our labs. And then link that nanoscale material structure to the activity of the material. And I think that is really important. And this is where I suppose the crux of catalysis is. This is where you get the most value out of it, is developing the structure activity relationship in a way that can help you predict what to do next. Now, when I say predict, there is a position, I call it the position at the top of the mountain. And people who are into computational chemistry love this idea. It was published in a review in ChemSoc few years ago now, where you can think about your chemical inputs, what type of reaction you want, what could be the possible steps, etc. Come up with some parameters surrounding that, and then predict what type of structure would do that based on information that was already available in the literature. And then you go into your computational chemistry suite, you use your DFT and etc. and you develop these simulations of different types of surfaces and how they interact and what products they make, etc. And then from that, you select a system which is very efficient, so either high conversion or high selectivity or both. And then you make that in a lab using some very complicated instruments, atomic layer deposition, some very expensive CVD stuff, maybe atom etching with some toxic chemicals. And then you end up with a system that you've engineered that's precise. We've put atoms in a precise way on a surface, and then you do the catalysis. This is what I call the Rolls Royce. If you have the time and effort to do that, that's fine. Most likely, most of us won't have the time or the effort to do that. It takes a number of years, usually more than a PhD, to do something like this. The other thing is that there are not many examples where this has actually worked out, in that the stuff that you get from the use of the computational chemistry suites, you can actually make that in a lab, and then when you do the reaction, it works. Okay, from designing solids, that's fine, but making those reactions work with those materials has proven to be a bit elusive in catalysis. So we decided that we would set our principles. These are our targets for all reactions, and then we'll work around these targets to see what materials we can get to work based on information already available in literature and the techniques that we currently have available to us here at the UWI. We want mild reaction conditions. Remember, it's green, so we want low temperature and moderate pressure. Benign solvents, usually I say water or nothing. Of course, it's not that clear cut. Sometimes you do need to use some organic solvent in there, but usually we try to stick to water, and we've been able to do that so far. The materials must be efficient, so that means high conversion or selectivity, and we prefer selectivity to conversion because selectivity tells us something about the active site that conversion doesn't. Turnover frequency should be high or appreciable. Low metal use, since these are metal nanoparticles that we're using for catalysis, and stable or reusable materials, which we check at the end, right? And we haven't paid enough attention to that, I suppose, but in the future we will. So we start off talking a little bit about toluene oxidation, and this is one of the Odyssey stories, since my PhD was not in toluene oxidation actually, but I think I got one of my best papers was in toluene oxidation, which actually happened to the very end of the PhD into the postdoctoral research, right? And the idea behind it was that the toluene molecule has this methyl moiety in it, and those CH bonds can be activated only in special systems. And so it's a link to methane oxidation because, of course, methane oxidation has the same CH bond, albeit the strength of that bond is a little different in methane versus toluene. But the general idea is that if you can activate one CH bond, you can probably activate the other one. The driver for this was commercial viability of the technology, since a few companies in Europe at the time wanted to know how to do better toluene oxidation to make chemicals for fragrance and flavor use. And it's a selectivity challenge because toluene, the CH3 goes to alcohol, to aldehyde, to acid, and then to esters. And of course, you can get carboxylation as well when you start to form those oxidation products. Again, the targets, solvent-free in this case, since toluene doesn't mix with water, right? Low temperature, low oxygen pressure, and high selectivity. In the literature, there was a number of systems that were used, and actually these systems seem to work really well. I mean, appreciable conversion. You can get good selectivity to benzoic acid, although benzaldehyde was the one that they wanted. And this seems to be good. People published, they got good papers out of it, plenty citations. However, when we did the reactions without a catalyst, just in the autoclave under the same conditions, as you can see here on this graph, this line that is pointing to with the red is the conversion. So you see we get about 16% conversion after 30 hours in the reactor, which is a long time, but without a catalyst present, and selectivity to this product here, which is the benzoic acid. So if we go back to the table, we see this is about 20%, and of course benzoic acid is being made. So in effect, these catalysts are not even active. It's the background reactions, the auto-oxidation reactions that are predominant in this system. Of course, once we've seen this, we understand, whoa, that's a lesson to be learned. Check the background reactions. Always check what is going on in your background. Make sure you know what your reaction system is. But obviously, this is an opportunity to develop a new material. My colleague did this work, Lokesh, who's now, I think he went back to India. He was in Sweden doing postdoctoral research here for a number of years. And they developed gold palladium catalysts for this reaction that worked at lower temperature, low oxygen pressures, did no decarboxylation reactions on the product, and so it's atom economic. And in this case, conversion was 99% after about 100 hours, but this is known to be a slow reaction. 99% is pretty high, especially if you have a very high selectivity to benzyl benzoate. Now, benzyl benzoate is an ester that comes from the benzoic acid plus the alcohol or the aldehyde. And there are obviously other mechanisms in which you can get the benzyl benzoate, other pathways as well. So this is not a desirable product per se, but of course you could do hydrolysis on it at the end if you wanted. The interesting part is that only catalysts prepared on carbon here showed this sort of activity selectivity relationship. So at the bottom of the side, you'll see that titanium is poor for this. And in the work I was doing at the time, I couldn't use carbon because every time I put the metals on carbon and I put it in the furnace to heat it up during the synthesis, the metals, because the particles are so small, in the presence of any oxygen at all in there, burns the carbon and decomposes it. And so I couldn't use carbon in my work, and he's published this in Science, so maybe I want to try it and see what I could get. And so I was using titanium and zeolites as my supports of choice for depositing metal nanoparticles. The key thing here is that in the carbon sample, and I'll show you this, I think I have some micrographs. In the carbon sample, the shape of the particle is important. So I did the same thing using palladium platinum, and turns out actually I was able to get the same result in terms of conversion in the same time of the reaction. And Lokesh actually did the reactions with my materials, and I was able to switch off the pathways to create the esters in this case. So the major product here would have been the benzoic acid. So it's different. And of course, at that point, the catalysis person says, oh, I need to find out what's happening with the surface. If I know how these particles are arranged on the surface, I'll understand how to do this reaction. Why is the platinum palladium working on titanium? But if I put it on carbon, it doesn't work very well. It turns out that the size and the composition is important, which I'll show you shortly. You can also do this reaction with TBHP. And this is another strange thing that happened in the lab. We went off for Easter vacation, and my colleague, Izam bin Mohammed, he had taken a bit of the catalyst. I said, test it for your reaction. So he's doing toluene with TBHP, so butyl hydrogen peroxide. And he left the catalyst in the toluene TBHP submix there in the fume hood, put a cap on the top of it, a piece of film, and left it and went off. Went back home, took a whole month off over Easter period, came back. And when we came back to the lab, we saw that the entire round bottom flask, because this was being done under low temperature and regular pressure, the entire flask was filled with crystals. I said, well, why is it crystallizing? So we obviously check it and dissolve this stuff and realize that it's actually filled with crystals of benzoic acid. No heat, just sitting there in the cool, and this is in in Cardiff, so it's about 15 degrees in springtime or so or less in that area. And so we then recognize that this catalyst must have actually quite high activity to do this. it turns out that the catalyst itself uses the TBHP, which is shown here. This is the catalyst that I'm making, but it doesn't actually start to use it after 40. So if you check the amount of oxygen in the product versus the oxygen that could have possibly come from the TBHP, you realize that oxygen is coming from somewhere else, and it turns out that it's coming from air. So this material activates molecular oxygen directly at quite low temperature. So we use this as the basis to continue some further reactions, some further investigations. And I wouldn't show that data when that has to wait till publications, whenever we finish that work to do it. But I will show you the data on the materials and what they look like. So here we're looking at the colloids. This is the gold palladium system that Lokesh published in Science, works very well. You can see that this is the colloid before you put it on the supports, when you make it in solution, right? When you put it on carbon, it retains the shape more or less. When you put it on titania, you can see that now part of the spherical particle becomes truncated. And you can see over here, there's some interaction between the particle and the surface. And this interaction is, of course, much better than the interaction of the particle with the carbon surface. The sizes are about the same. I mean, this one is a little larger in the titania example, but the composition is the same in that the particles have both gold and palladium in them. And you can do an EDAX analysis to support that. In the systems that we do, and the same methodology that's used to make these catalysts, the students all use the same methodology now. So this is the same thing we'll be talking about over and over. The palladium, platinum, and the mixture of them. And so what we see, of course, the particles are quite small. I mean, less than 3 nanometers in all cases. Interestingly, we can actually see some things. So this dotted arrow, may not be too clear on your screen, would have pointed in the publication to single atoms, and the solid arrows to sub-nanometer clusters. So this is a method in which we can deposit very, very small particles on the surface. And the particles tend to be mixed, so we can get a homogeneous alloy. What this is showing here is a particle, you do an EDS analysis, and you see platinum and palladium in the particle. So it's actually mixed alloy, and that works really well for that reaction. We will, oops, great. So I'm going to speed up a little bit, time is running. The materials do really good hydrogenation chemistry as well, it turns out. So the same catalysts work for oxidation and hydrogenation, which is normally not the case in catalysis. The first reaction we looked at was levulinic acid, because it's one of those platform molecules that was on the top 20 list back in the day for biomass-derived molecules that have potential to replace fossil fuel-based molecules as coming from fossil fuel-based resources, and in particular making gamma-valerolactone and obviously diols and MTHF, which is a fuel blender itself, or used for solvents, for production of cosmetic materials, etc. Now, usually you have to have very high pressure of hydrogen, because levulinic acid is not so easy to work with, and obviously high temperature. And depending on your catalysis system, the levulinic acid can actually dissolve your catalyst. So that's also a consideration. We did this work with the same materials and found that platinum was really good. Platinum, palladium wasn't as good, but also had high selectivity. Palladium didn't work very well unless you cranked up the temperature a lot here. And this is a solventless, a solvent system of water, where you dissolve levulinic acid in water at high weight % of the substrate and using a very small amount of catalyst, right? So the turnover number is actually quite high. If we leave this for longer, we see that we get further products, which mean, of course, this reaction is only in 4 hours. Typically, these sorts of reactions are using 8 to 16 hours for materials which are very difficult to convert. And so we can actually get fuel blenders, we can get materials to use for use as solvents or in other synthesis reactions in this way. So this was published. That's fine. And so we went on to see what else we could do with it. It turns out that the material is actually stable without rehydrogenation, and that was quite a surprise. However, we've not got any further information on in terms of in situ characterization. So that means operando experiments where we run the experiment and at the same time perform the materials characterization. And hopefully one day we'll be able to get onto that. So it's a good system and it works well. The question is, from that hydrogenation, my question always was, could I do better? So I have mild reaction conditions, the solvent is okay, the materials seem to be quite efficient, they're stable, but there's a problem. The problem is that I'm not necessarily using renewable materials all the way. So went back to ideation board, hydrogen with any substrate, levulinic acid, furfural, whatever, in water, and we can actually get the good selectivity to products, and we're using furfural because we're going to switch to that now. The hydrogen is coming from natural gas primarily, and we don't want that, of course, because the co-product is CO or CO2, depending on how they get the hydrogen out. And of course, natural gas means that we have to have the resource in order to do the reaction. We could do better selectivity over here, and I'll show you some data on that. So we thought, how could we get hydrogen? Well, renewable hydrogen that's the fad. Everybody's talking about renewable hydrogen. There are megawatt hydrogen projects going on around the world, tens or hundreds of millions of dollars in hydrogen research into hydrogen, how hydrogen can be used to validate a hydrogen economy concept. And so we thought about what are the ways we can get this hydrogen to do the reaction. We can use electrolysis. Every chemist knows about that, water splitting with electrons flowing from external circuit. We could do hydrogen carriers like amines, for example, ammonia, alcohol, some of which could be renewable, and do catalytic transfer hydrogenation, so transfer the hydrogen to the molecule we want. We could do some in situ electrochemical, so basically the electrolysis and the electrochemical reduction is happening at the same time. All of these systems require electricity and heat. And electricity, therefore, has to be renewable. And to create renewable power, you do need to sacrifice some of that power. And so inherently, this system is not a pinnacle system, is not the best-in-class system, because you're going to have losses of electrons all the way through making the product. So we decided actually that we would use water splitting, and I want to show you that really quickly. Do photon-driven water splitting is what our new fashion is in the lab, besides the thermocatalytic work that we continue to do. And we're using titanium as a semiconductor with nanoparticles. And the systems work to make hydrogen. We know that, and now we're trying to figure out, do these same systems work to make the products as well as making the hydrogen that we need? So many of you would be familiar with this sort of diagram. Light hits a semiconductor, the electron moves from the valence to the conductance band. We get an excited electron, which can do some work here. In this case, we want to make hydrogen gas. And we have a hole, which can also do some work here, in which case we want to make oxygen, if we were doing overall water splitting. We don't want to do that, of course. We want to use the hydrogen selectively and let something else be the scavenger for the whole. In the literature, over the last few years, actually, people have published this concept where they can create hydrogen from water and at the same time do some oxidation of another molecule that was in solution. So example over here is the hydroxymethyl furfural example over here. They're using isopropanol as a hydrogen donor to do levulinic acid to GVL. In the bottom, they have glycerol, and we're interested in glycerol. And doing oxidation of glycerol using oxygen. So this is oxidation hydrogenation. And why this is such a nice platform, I think, is because you can tailor the materials to do, you can tailor the materials to do a few things at the same time. And that's really good in terms of being able to do a one-pot reaction, increase selectivity, be able to have multi-component reactions being done in the same system selectively. So yes, it's been done, and this is preliminary data, it's top secret, so I'm not showing you all of the data. We actually have tested these materials, a variety of them. You see the type of metals here, maximum 1 weight % overall for any of the combinations, platinum, palladium, nickel, or iridium, and got really good data on hydrogen production, right? So the platinum and the palladium do above 1% hydrogen in the gas phase. Now this, if you compare to literature, under the conditions that we use, is extremely high conversion rates of the photons going to make hydrogen gas. And of course, if we're doing this in a reactor at room temperature with water, the scavenger is ethanol, with a very small amount, 25 milligrams of a 1 weight % catalyst, it's a good basis for us to do our reactions, our biomass conversion reactions at the same time. So that's what we're doing now. If I get time, I love this video, I'll play it at the end. So I'll just show you some data on furfural. Furfural hydrogenation is a bit interesting from the standpoint of the amount of products and pathways there are from furfural to its products. And the key here is, of course, which product has the value for you. And so if you have a catalyst that makes furfural alcohol, then your industry or your business proposition has to be furfural alcohol. If you want to make cyclopentanol, cyclopentanone, or any of the diols, then your business proposition has to be towards that. Now, interestingly, of course, we want to make catalysts that can do the different reactions selectively. So you can take the raw material and in your industrial plant, transform it into anything that sells at the time. And so you don't have to pin your industrial strategy to a particular end molecule because you can make all of them selectively. So the idea here is that we want to make cheaper catalysts that don't contain too much of the precious metals, since the precious metal catalysts have been the ones that have been used ubiquitously in this area. And to do that, we're thinking we're going to use bimetallics. We're going to switch supports from traditional types of supports like carbon in order to deposit those bimetallics and make them work. And using water as a solvent or using some renewable hydrogen source, which is the photocatalysis work that is currently ongoing. This data is from my student, and she will soon be submitting her PhD thesis, I believe, sometime this year. And so this is her extremely good data. I'm really happy with this data, where she's taken ruthenium, copper, and iron, deposited on titanium and also titanate nanowires, and was able to tune the selectivity. So here we see moderate conversion for ruthenium, high conversion, but look, too many things going on here. All of this is going on, too many products. When we start to mix these metals together, the selectivity profile changes. And so we could tailor what we're doing to make a particular product. Interestingly, I love the copper iron catalyst because although the conversion is a little low, the selectivity is actually quite high to furfural alcohol. When we take the same methodology, the same metal species, and we then decide to deposit it on titanate nanowires, we get a completely different story. In the bimetallics now, we have really good selectivity to furfural alcohol, which indicates to us that there is something going on with the metals on the surface, and probably these metals are mixed as alloys on the surface, and therefore we need to study that further. Also interesting in this is that the iron catalyst, although it has low conversion, is actually active and at such low weight %, the iron and the copper catalyst. And that's quite interesting, and we're trying to understand why that is the case. Usually people are using 5% and up of the metal, and obviously putting quite a lot of catalysts in there to do that. Ruthenium, I call it, ruthenium is always just a mess. Ruthenium makes all sorts of stuff. It's difficult to control what ruthenium does. However, when we start to mix those metals together, we have control. And in this way, the catalyst synthesis affects the reactions profoundly from the standpoint of the deposition of the metals, but also the production of the support materials and what the support is doing. So this is also a support effect, as well as a metal nanoparticle size, shape, electronic character effect. And Marvidine, I think we have 8 minutes left. Is that correct?
Yes, just about.
So I'm actually going to skip over the beautiful TEM a little bit to give you some ones that are more easy to explain and understand. These are just some micrographs of catalysts that Nakisha has made, and she'll be doing the final work on this soon, because we actually do need to see what those very, very small particles are on the surface they're below 10 nanometers. Some cases, we think we have probably even single atoms and sub-nanometer clusters on the surface. But I just want to switch for a minute to some of the other materials, because this ties into what we're doing photocatalysis. We're making lots of nanotubes, nanowires, nano everything in the lab. And these micrographs are actually taken here in the spectroscopy unit, the microscopy unit in Mount Hope, which is run out of the Department of Physics. Yes, physics. And so you can see we're actually making nanotubes. It's really, really nice work here. On the beginning slide, that catalyst that I was on the beginning, my title slide, was actually from Nikisha's work, which is a nano rod or nano wire, if you want to call it nano wire, that had nanotubes in it, which inspired me to look further into this work. And we're also doing things like depositing. This is a picture of carbon doping. So in this one here, if you look really close, you can see some very tiny spheres, circular areas that are dark. And that's actually carbon that's being deposited as maybe carbon nanoparticles or on the surface of this rod. Things like sulfur doping. This is an example of sulfur doping, actually, where the sulfur is actually in the middle. That's why this area looks darker. Usually the outsides of the tubes look darker when it's hollow, and the inside is lighter, but here it's reversed because the sulfur is actually on the inside. And these materials have photocatalytic uses. Of course, we need a better microscope to get really, really good images, I think, some of these systems, but we're working on that with collaborators, hopefully in the near future. So the work is very varied. We have a few things in the pot. It's all mixed up, but it's all related to each other because it's hydrogenation and it's oxidation. The material design strategy is the same, which means that we're putting the metal nanoparticles on the surface in the same way, and therefore the systems are related in that way. Also, the learnings from a hydrogenation system with levulinic acid also apply to maybe furfural being hydrogenated or another hydrogenation reaction. And what we're trying to do is tie up all of those lessons into photocatalysis to move away from thermocatalysis. So we don't want it to be heat driven. We want it to be light driven, because that's where we're going with it. It's green. And so the current projects that we have, HMF oxidation using air, water, and sunlight. That's going to be a nice one when my student Sean gets to it. I don't know if he's on now. Photocatalytic furfural hydrogenation, which we're pretty certain is going to work as well. And we already have some information on the glycerol upgrading using photocatalysis and using that for levulinic acid hydrogenation. So it seems as if the skies are blue, and hopefully if the equipment keeps working, the skies will continue to be blue. And we have another area that we're looking at too, which is off this topic, but it's using 3D virtual reality in teaching and learning of chemistry, which will be another talk we'll give another time when we get a little further into that project and have some value to add to the academic community on the ideas that we're using there. So it's been an odyssey of too many things for 1 hour, I think, right? Probably. And I do have a peccant for talking people all the way to being brain dead with too much information. But I do want to have a slide for acknowledgements and say that a lot of people have been involved in this work, and a lot of people will continue to be involved in our work because we believe in collaboration. We believe in talking to each other, discussing things with each other. The human being has a really nice thing that they do. They can speak, and it's wonderful, the power of speech. Be able to talk to people, come to conclusions, get new ideas, connect with people, and we really believe in connections. And so this acknowledgements slide is going to be much longer as time goes by, of course. And then, of course, I want to thank you for listening to the presentation, and I will field any questions for the few minutes that we have, apologizing for moving a little slow in the start and not being able to give you a bit more meat on the characterization, which some of you I know would be appreciative of. Thank you so much for the seminar. Marvadine, over to you.
Thank you so much, Dr. Ford. The Odyssey continues. So we can continue next week, Michael. I mean, we still have some slots in the seminar to fill up. So you tell us.
Next semester, Marvadine.
All right. Once again, Dr. Ford, we want to thank you for this journey. You know, really some exciting things going on, and we want to open the floor right now for some questions. We do have a few minutes, so let me see if there are any hands going up. I have Dr. Taylor's hand is up, and so I was looking if we have anybody from Mona first in Dr. Taylor, but your hand is up, Dr. Taylor, so go right ahead, please.
Thank you very much, Marvadine. And Michael, thanks for sharing a bit of your Odyssey with us. It seems very exciting, a journey that you've had and continue to have. I just want to ask something about your nano catalysts in particular. To what extent does the size influence the activity? Because of course, you know that for these nanostructures in general, size does play a part. And have you been able to sort of control the size distribution of your catalysts embedded on the substrates or on the supports? And to what extent can you correlate the relationship of size with functionality?
Michael?
The way that we deposit the particles using a vapor deposition technique, what we've found is that we've checked copper, iron, palladium, platinum, I think as well, one or two other metals have been checked, and you always get very small particles. And this is actually, if you look at the particle size distribution, it's a tight distribution. But what we do see here in all cases, and I wanted to show the video for another palladium catalyst in which we have lots of single atoms on the surface, we actually get single atoms and sub-nanometer clusters. So for us, we actually need to understand, are these sub-nanometer clusters and single atoms active? In the catalysis literature, of course, there's always a volcano plot relationship with size. So there's some sweet spot in the size that works best for your catalyst, and it depends on the reaction. So some reactions are very size sensitive, and many of the types of reactions people have been doing, for example, with CO2, hydrogenation, for example, is a good one for size, where if you have a copper particle that's 5 nanometers to 10 nanometers, it doesn't do the hydrogenation of CO2 very well. But if you have a particle that's between 10 and 20, it does it good. And if you go above 20, it doesn't. And so that's a reaction we actually have to try since we have these small particles and see if that holds for us. But in terms of the relationship, we haven't been able to pin it down because we can only make small. We haven't been able to make larger particles. The methods that make larger particles reducibly also put other species on the surface of the catalyst. And then you have another parameter to think about.
Okay, thank you, Dr. Ford. I see Dr. Min, Zayar Min, his hand is up. Go ahead, Dr. Min.
Hi, Dr. Ford, how are you doing?
Hello.
Hi, I just wanted to ask, these nanocatalysts, these nanoparticles that you're showing right now, do you know if there's been any efforts or if there have been any work where they try to kind of distribute it in scaffoldings or frameworks or MOFs or anything like that to test if they have an increased efficiency or effectiveness, things like that?
Okay. The first thing I will say is that the systems also work if you use microporous materials like zeolites. So if you put the metals on zeolites, you get the same type of particle sizes. Of course, when you have these pores, it may restrict it to being even smaller particles, a tighter distribution. In terms of MOFs, no. What people have been doing with MOFs, though, is putting metals, making nanoparticles from the MOFs themselves. So decomposing the MOF and ending up with small nanoparticles, which they can then deposit on something else, which is an interesting strategy because it seems to be roundabout to me to make a beautiful MOF and then just degrade it to make nanoparticles. One of the issues here, at least with our technique, will be the thermal stability of the MOF, because we normally treat these between 400 to 500 degrees to get these small particles, because it's a vapor deposition technique. So if you had a MOF that was really stable, you could try it. Alternatively, there are other mechanisms, and I see people have done incipient wetness catalysts, I think, and solid mobilized catalysts on MOFs, because those don't require you to have high temperature treatments necessarily. So it is a possibility, but we haven't tried that as yet. In my MOF stuff, I'm interested in, can I put a single metal in the center of the unit in the MOF, and is that metal active? Because the site to reach that metal is open. So there's some space, things come in, they react, they go out. So basically, can I make a MOF that looks like a zeolite? That's where I would go with that sort of research. Not there yet. I need to get another student for that in the future. Hopefully not the too distant future.
That sounds really interesting, the report. Yeah, I mean, there are a couple of MOFs. Even our group also have a couple of MOFs with that high stability. But I was also thinking of it. I'm sorry about the noise in the back. I was also thinking about it in terms of, like, if you can deposit, rather than nanosizing the MOFs themselves, if you can deposit these nanoparticles within the frameworks themselves, then you would have, I would imagine you have a greater surface area and a greater efficiency in catalytic activity. So I was just wondering about that, but I think you pretty much answered.
That would be true. That would be true.
And I suppose the sizes would be quite relevant here.
Yes.
Yes.
And
I mean,
the issue there, really, of course, would be when you do depends on the type of catalysis that you're doing, the solvent system, the nanoparticles may come out of the system. And that is always a consideration in there. But it is entirely possible to deposit these on MOFs. And we'll be happy to do that as well.
Thank you, gentlemen. Dr. Taylor has some samples down there at the unit. It's been there for a while. My samples. These are MOFs that we have loaded metal nanoparticles inside there. Michael, you can go pick them up for me 1 year or 2 years later, and we can do some things with them. This is the idea. So metal nanoparticles loaded inside our MOFs. Our MOFs, we do have some that are stable at that temperature and above 500. So, that's all right. So let's, Richard, please check on those for me to Michael. Are there any other questions out there from anybody else? We do have a number of people. We have had about 45 or so participants. Any more questions? Any comments? Anybody? Nobody? Okay. All right. Michael, I think either things were very clear or people are very busy and very tired. And it is after 12. It's 12:05, I think.
It's lunchtime, your time, yes. And catalysis it's a mind game.
And maybe that is a part of the reason, because there's so many things going on, so many meetings and so. But indeed, the MOFs have evolved as one of the most prolific supports in heterogeneous catalysis, and it is something that they have record-breaking porosities and unprecedented tunability. And I've spoken to you about this, so definitely we should be looking to doing some things together. I want to thank you, Dr. Ford, for all that you do and for sharing with us this morning. I want to thank all the colleagues who have found the time to come over, all the students who are here from Jamaica and across the Caribbean. And I want to wish you guys keep safe, and we'll see you again next week right here in our Thursday seminar series. Have a good afternoon, everybody.
Okay, I do promise to test some of your MOFs.
Thank you, sir. Dr. Taylor, you're still there?
I am, Marvin, yes.
Terry, you can stop the recording. No, please. Where are my samples, sir?